go through the proof for it. But Theorem 318 tells me that as long as b is greater than 0, then for all x's, if you're taking the derivative of a number, a positive number, raised to a variable, then the derivative of that, the pattern for that, okay, Megan, is the number itself, just written down again just like it is, times the ln of the number being raised to the variable. Okay, that's just the pattern. If it's a number raised to a power, then the derivative is the number raised to the power still, but it's multiplied by the ln of the number. So example 2, if we have that f of x is 3 raised to the x. This follows my pattern, right? It's just a number raised to the variable. Yes? So the first derivative, I just write it down again just like it is. So I've got 3 to the x, but then I multiply it by the ln of 3, the number. That's it. That's how you do it. Yep, just plug stuff in to get that one. Now on the next one, you have a little bit more, but it works pretty much the same way. So they tell me that g of t is equal to 108 times 2 raised to the t over 12. It's multiplied by a number, but what do I know about all of my derivatives that I had so far that had a coefficient? You just bring it down, right? Just bring the coefficient down. So when I take the derivative of g, then I'm just going to bring down the 108 just like I've been doing because it's just a coefficient and it's going to work that way every time. Then to the t over 12, but I do have a problem now because I also need to do the chain rule here, right? Yep. So I need the derivative of t over 12, which would be 1 over 12, right? Because that's just like 1 over 12 times t. So it'd just be the coefficient times the ln of the 2. No, not because the variable's in the exponent. Anytime the variable's in the exponent, I can't use the power rule like we've done before. And now I need to simplify this. Yeah, so 108 times 12 would be 9. And then you can move the ln of 2 up in the front if you want it, or you can leave it back behind. Well, you can stick it in the calculator if you want to. You could have one of those if you wanted it. But you're the one that said if I had one of those. All right. Okay. Okay. So you had a question? Oh. Well, actually, I just took Blake's word for it. You question Lake? All right. Okie dokie. So anyway, here's just another example. This is the quick check in your book. And it is quick check number 3. We didn't do 1 and 2. I didn't see them. Okay, it says suppose A is equal to 500 times 1.045 raised to the t power. It wants us to find the derivative of A with respect to t. Okay, so what are we going to do? Got to bring 500 down because it's just a coefficient. And I don't have to worry about the derivative of the exponent this time because the exponent is just t, and the derivative of that's 1. Okay? Any questions? Yes, that's it. Right. Okay, so let's just look at some more of these. Because I want to show you, I want to remind you about the difference, because somebody said a while ago, do I just use the power rule? So I'm going to kind of mix you up a few, where sometimes we use the power rule and sometimes we use this new exponent rule. Okay, thank you. It's going to be that way on the test, right? Okay, so this is y is equal to x to pi. Is pi a variable or is pi a number? Pi is a number. So in this case, I have the variable raised to a number. So which rule am I going to use? The power rule. So the derivative of this is going to be, I'm going to bring down the exponent, which is pi. I'm going to have the argument, which is x, to the pi minus 1 power. Okay? And I don't have to take, it's not a chain rule because the argument's not any, I mean, the thing's being raised to the power is not anything but x, right? The derivative of that's just a 1, so I don't have to worry about it. My pie is ugly to you. Oh, whatever. Okay, so are we good? All right, let's look at B. What if I had written it this way, though? Now we have to use the exponential rule because this is a number raised to a variable. So the first derivative of this is what? Pi to the x, right? And then I have to take the ln of pi. Take the ln of the number part. Good? That's all there is to it. Let me give you another one. It's an interesting one. Y is equal to x squared plus 4 raised to the e power. Yeah, this is C in the same example. Now, this is what? Chain rule, right? That is a chain rule going. But just simply because the thing being raised to the number power is more than just x, right? So I'm not going to use the power rule, though. Everybody see that? I'm not using the power rule. Why? No. E is a number, so what am I going to be doing? The power rule. Good. I know. I was seeing if y'all were listening. I'm sorry. All right. I was seeing if y'all were paying attention. So we're going to bring the E down. Wait. Whatever E minus 1 is, don't forget to write that down since we're leaving it. Excellent job. So we are using the power rule because the variable's in the argument and the exponent is a number. Ln of a number is a number. Ln of x is not a number. Yep, E is an. Those are my two irrational numbers that we have found through experimentation that we know exist out there, besides the irrational numbers that are the square roots of non-perfect squares. Right. Yes. There's no ln in my derivative because this is not a variable, it's a number. You got to be paying attention. E and pi are not variables. They're numbers. Okay? Remember that when you're doing tests and homework and all that other stuff. Okay? Alrighty then. So, example 5. That we want to be able to actually be able to find horizontal tangent lines. Now we've talked about finding equations of lines a whole lot, but why do we ever find the horizontal tangent lines? Because I tell you too, that's a good reason. But what is going on when a line is the tangent line's horizontal? It's touching at a turning point, right? It's a place where it's like it's been going up and it's turned around and going down, and that's when my slope is exactly 0, right? And so a horizontal tangent line is one that's got m equals 0. Okay, so that's the connection with what we've been doing. And we have done this before, but I just want to always remind you because y'all forget from one day to the next. Okay, so what we're doing in example 5 is we're going to decide, does the equation f of x equal x raised to the x, as long as x is greater than 0, have, or does it, would that be have or has? Does this equation have, there we go, any horizontal tangent lines? So on a test, that's a possibility of a question. It's going to give you a function and ask you to determine whether or not this thing has any horizontal tangent lines. So, how do you decide that? You want to know, is the first derivative ever equal to 0? What's greater than 0? No. This gives me the right. Yes. Okay. And since I have the right. Okay, so this doesn't work for us. We don't have anything where it's a variable raised to a variable. Right? So I'm going to rewrite that as e to the x times the ln of x. Using that rule that we had before. Okay? Do you want me to go through the process of how that came from? Okay. X to the x can be rewritten as e to the ln of x to the x, right? And then I can bring that x down in front, so it becomes e to the x times the ln of x. Yes, because e is just a number. All right? Well, the reason it is because we just got through saying that x is a number greater than 0, so I can use it. Yeah? Yeah. Remember, if I have the ln of an argument that's being raised to a power, then one of my properties that I have says I can bring the exponent down as a multiplying front. Okay? Are we good? So now I have this in a form where I can actually take a derivative.